So as announced, I will talk this morning about aleatoric and epistemic uncertainty. Let's start with a couple of motivating examples. So I would like to start with the questions, are AI systems trustworthy nowadays? I think many of you in the room would agree that the answer to that question would be no. And I'm giving you here 3 examples of the popular media that kind of confirm this. So the first example is about AI models that have been constructed during the COVID pandemic. And this article claims that none of these AI models actually really has helped to predict the number of cases that were occurring in those times. Second example is an example a bit more recent, where a lawyer has been using ChatGPT in the courtroom, and the judge discovered it. Actually, this lawyer was kind of making claims for a legal case based on things that ChatGPT had produced, and the judge said, okay, what you're claiming here is nonsense. This doesn't make sense. This is actually not a legal claim, a correct legal claim that you make here, and this lawyer got punished for it. Third example is an example of a real estate company in the US that got bankrupt recently because they were using AI models to predict the house prices of real estate. And their idea was with AI, we're going to kind of build a system that's able to predict what the house price of a house is, and then we're going to buy all these houses, and then later on we might maybe sell them for a higher price, in the sense that if the AI model was predicting, okay, this house has like this value, but on the website the value of the house was kind of cheaper, then they said, okay, let's invest in it. But this AI system was kind of overestimating the house price, so at the end the company got bankrupt. These are 3 examples where AI systems are not trustworthy, but these are also 3 examples where they are not trustworthy because those AI systems are not representing their uncertainty in a correct way. And having a correct representation of your uncertainty is one of the key assets to make trustworthy AI systems. So how would this uncertainty be represented in its most basic form? This would be with a probabilistic model, things that all of you will know. Let's say, for example, you have images here. They're from the medical domain. There are some patients that have a disease versus patients that don't have a disease. You feed these images into a neural network, and then out of the neural network comes a probability that says whether a given patient has the disease or not. Here in this case, probability of 0.8 that the person has the disease, and 0.2 that the person doesn't have the disease. That's kind of the most simple representation to represent uncertainty in an AI system, but as I will explain in my tutorial today, this might not be enough in order to get trustworthy predictions. So in general, let's start with a couple of basic insights. What we want to have is an AI system that not should only make accurate predictions, but it should also be able to tell, like humans, what it doesn't know. Like a human will typically say, if you're not an expert on a situation, if I ask you to, for example, Christopher, if I ask you to classify, I don't know, images of specific insects, and you're not an expert on insects, you're going to say, I'm not going to do this because I don't have enough knowledge of it. Actually, we want an AI system also to be able to do that. And to do that, we will need a representation of this uncertainty. So we will need specific models that are able to represent this uncertainty. And we will also need some kind of measure, a quantification of this uncertainty that says, okay, how certain am I about my prediction? And what also plays a role in there, that will be the learning algorithm. The learning algorithm that we choose, a neural network versus a decision tree versus something else, will also have a major impact on how we represent this uncertainty. Those 2 things, they have an interplay with each other. And then the last thing is that we should be able to distinguish different types of uncertainty. So recently, there has been quite some work on distinguishing 2 types of uncertainty, aleatoric and epistemic uncertainty. Aleatoric uncertainty is considered as uncertainty that is not reducible by collecting more data, whereas epistemic uncertainty is data that is more reducible. And actually, together with Eike Hullermeier, so normally I teach this tutorial together with Eike, but he could make it here today, so today I'm going to do it alone. Together with Eike Hullermeier, we had in 2021 an article that gave an introduction to this type of this entanglement of uncertainty, and this article got picked up quite well in recent years. So that brings me a bit to the overview of this tutorial. What I'm going to talk with you in the next 2.5 hours is actually 3 parts. So in the first part, I'm going to tell you a bit more about this distinguishment of aleatoric and epistemic uncertainty, how we're going to do this, what are the basic insights in there. And then in the second part, I'm going to talk about first-order uncertainty representations. I will explain at that stage what I mean with that. The last part of the tutorial will then be about second-order uncertainty representations, and we will conclude with some take-home messages and some open issues in the field. So I'm planning to have like 2 short breaks somewhere in between. We'll see how quickly we evolve. But probably in the middle of the first-order uncertainty representations, we'll have a first break, and then when we start with the second-order uncertainty representations, we will have a second little break. Okay, but let's first start a bit more about what is this difference between aleatoric and epistemic uncertainty. So I would like to start with a simple experiment. I ask a couple of you in the room to throw a coin in the air, and we want to predict the outcome, whether it's heads or tails. Now, as you might know, this is kind of unpredictable. Let's say I ask it to you, Christopher, and also ask it to a few other people. Your age or whatever, or the information I have about you will not give us further insight into what the outcome of this experiment might be. So this is considered as aleatoric uncertainty. This uncertainty is not reducible if I ask you to throw up the coin 10 times or 20 times. The only thing you will discover is that hopefully it's a fair coin. Maybe it might be an unfair coin, but like in most cases, it will be a fair coin, and the probability of heads will be 50%. The probability of tails will be also 50%. But let's now imagine the following experiment. I ask a couple of people in the room to throw up a coin, and then we're going to put a camera on you that's going to register the experiment. And based on that, we want to kind of, from the video afterwards, we want to detect whether it was heads or tails. So you throw the coin in the air, this is registered, the process, and there's a movie recorded. This is now a process of epistemic uncertainty. We will be able to predict, if we have enough movies, we will be able to predict with 100% certainty whether it's a coin, whether it's heads or tails that was thrown. Of course, the camera needs to be in the right angle. So this is epistemic uncertainty because if we collect more data, if we have more movies of more people here in the room, we will be able to distinguish and to diminish this type of uncertainty. So what are the basic properties of those 2 types of uncertainty? So first of all, in terms of sample size, the way I look at aleatoric uncertainty is when the sample size increases, then your aleatoric uncertainty is going to converge to a certain number. Gradually, we will discover that the coin has a probability of 50% for heads and 50% for tails. Whereas for epistemic uncertainty, when your sample size increases, it's uncertainty that should go down in the limit when we have actually access to the underlying distribution of the data, then this uncertainty should go to 0. Now, if the complexity of our predictions increases, so if you go beyond classical binary classification problems, let's say multi-class classification problems with a lot of classes or complex classification problems, typically what happens is that the 2 types of uncertainty will go up when we have more complex decisions. For more complex decisions, we need more data, so for that, epistemic uncertainty goes up, but there's also, from the features that we might have in our problem, they're also more difficult to predict, so also your aleatoric uncertainty will go up. And then the third dimension that I find important is what if we collect additional features? If we have like more data to our disposal, like this expensive camera here, maybe we had a cheap camera, we replace it by a more expensive camera, then typically our aleatoric uncertainty will go down in such situations, whereas the epistemic uncertainty typically will go up again because we have more information available, so we need a higher sample size in order to get useful information out of this higher dimensional feature space. So the way I look at aleatoric and epistemic uncertainty is that about aleatoric uncertainty, you can't say too much yet as long as your epistemic uncertainty is high. So here is an example. We have a binary classification problem, and let's say we want to make a prediction for this instance over here. At this stage, there's not that many other instances in the neighborhood of that instances, so our epistemic uncertainty is high at this moment. We can't say a lot about the aleatoric uncertainty. So when we discover like more data, let's say we increase our sample size and we get this data set, now we have discovered that this observation is an observation of high aleatoric uncertainty. In this region of the space, the two classes overlap quite heavily, and for that, it's difficult to make a correct prediction. So aleatoric uncertainty, you can only say something about it, provided that your epistemic uncertainty is small enough. So that's one property. Then a second property is the kind of models that you consider. Let's think about this simple regression problem. I have, the only thing I'm mentioning to you for the moment is we have a moving object. It moves over time, so on the horizontal axis I have time, and we're going to measure the vertical position of that object. Let's say, for example, it's an airplane or a drone, and this is the vertical position over time. Can we make a prediction for this? Are we very certain what the next time point it will be? Probably not if we don't take any further assumptions. But if we know, for example, that this is a damped oscillator, a damped spring, then, based on physics, there might be only one function that fits the data. And in that case, our uncertainty will be very low. So the point I want to make here is that the model class that you consider takes also a major role in how you're going to represent your uncertainty. Whereas without this domain knowledge, our uncertainty was very high. With the domain knowledge that we have, provided, of course, that this domain knowledge is correct, our uncertainty becomes much lower. And if I understood correctly, this afternoon there's going to be a tutorial where exactly this type of models, physics-based models, are going to be further discussed. Then a third assumption that we need to take is whether we are in a closed world or in an open world. So let's take again this binary classification setting. I have here the red points and the black points. And I get a new object over there, the green one. We have to think, okay, is it going to be one of those two classes, or might it perhaps be a third class that we haven't seen yet? So if we are in an open world, then we might use this uncertainty to actually predict that this is a new class. And actually, a lot of those methods that disentangle epistemic and aleatoric uncertainty, as I will explain later, these methods will in principle be used quite often to make predictions for new classes that we haven't seen before, like, for example, in out-of-distribution detection. I will come back to that in the last part of the tutorial. Okay, let's represent things a bit more formally. So, with this aleatoric uncertainty, we're usually in a machine learning setup, in a supervised machine learning setup, where we assume an underlying data distribution. Maybe I'll use the mouse for it. So we assume an underlying data distribution P, which is a joint distribution over the input space and the output space. So I will consider in this tutorial both binary classification problems, multi-class classification problems, and regression problems. And so with this joint distribution, we have an associated conditional distribution of y given x that you just compute based on standard probability theory, in fact. Now, this conditional distribution, usually this is a distribution that assigns different masses to different y's. So it's not a degenerate distribution. And this distribution is a distribution that is going to represent our aleatoric uncertainty on the population level. So we assume an underlying distribution from which the data is generated. And because this py given x is a distribution that has a certain entropy, that is a distribution that assigns different probabilities to different labels, there we have some aleatoric uncertainty present. Now, in addition, we will have epistemic uncertainty. And what is our epistemic uncertainty going to be on a formal level? On a formal level, it's going to be the difference between this true p that we don't know and the p that we're going to estimate. I will use in the presentation p hat. So this is going to be an estimator. So usually with a supervised learning model, I will also use this notation here. We have a model that is a mapping from x to p over y, the set of probability distributions on the label space. And so this gives me this predicted py given x. And usually it's not identical to this true py given x. So that is going to be our epistemic uncertainty, basically. Okay, and that brings me now to the different ways of representing uncertainty. So in this tutorial, we have always made a distinction between first-order representations and second-order representations. You also have zero-order representations, and the kind of plots we use for that are these simplex plots. So this is here an example with 3 classes. So how do you have to interpret such a simplex plot? There's different ways to make those plots. So we have probability distributions in the simplex. And so this vertex here represents class 1, this vertex represents class 2, and this vertex represents class 3. So for a given instance, we have the true underlying probability distribution, which could be this one. So we have here 1, 2, 3 lines for class 1. So this is a probability of 0.3 for class 1. And then for class 2, you have to follow this, and so on. Now, if you have a deterministic predictor, there's still like commercial software. There's not that many models in academics that are deterministic predictors. But if you have a deterministic predictor, you would just predict one of the classes. Let's say I predict class 1 over here, or you could predict class 2, or you could predict class 3. Now, most of the models we use nowadays, like in deep learning, in neural networks, you always get a probability out of it. So we call that a probabilistic predictor. So for example, you predict this probability over here for the 3 classes. I have 0.5 for class 1. I have 0.3 for class 2. So you just follow 1, 2, 3 lines on this axis. It gives you the 0.3. And then the 0.2 for the third class. So they have to sum up to 1. Those 3 probabilities. And then here we can already see, okay, our aleatoric uncertainty and our epistemic uncertainty, because the red point is not identical to the green point, so we might have an estimation that's wrong. The red point is not exactly the same as the green point, so because of that you have some epistemic uncertainty here. Now, with these models, you can't do further than that. You can just represent your aleatoric uncertainty in the form of a probability distribution. Now, with the second-order models, which are becoming more popular, these are models that are, in addition, modeling a distribution over this probability vector, a second-order distribution. So your first-order distribution is your probability vector that you model. Your second-order distribution is a distribution over this vector. Like, I think that my probability is this one, this vector, but I'm not sure about it, so I'm going to model a distribution over it. And that's going to be like, for the last part of the presentation, we're going to focus on these models. In the next hour, I will mainly focus on those probabilistic predictors, and then in the last part of the tutorial, I will focus on these predictors. So formally, what does it mean if you have a deterministic predictor? You have a mapping from the input space to the label space. In the case of a probabilistic predictor, your machine learning model is a mapping from the input space to the set of probability distributions over the label space. And in the case of a second-order predictor, your model is a mapping from the input space to the set of second-order distributions. So the set of distributions over the label space of Y, those second-order distributions. Okay, so for the next hour or 45 minutes, I'm going to talk about first-order uncertainty representations. And I want to make a distinction between two types of representations. Either we're going to represent our uncertainty by means of probabilities, like on the previous slide, or we're going to represent them by means of sets. Both are nowadays quite popular in machine learning. I will mainly explain these for classification, and then in the last part, I will make the extension for regression. For regression, there are similar ideas, but there are also some differences, so I will have a separate section about that. Okay, probability distributions. So let's talk about some models that produce probability distributions. Most of these models you will know. Let's say, for example, a decision tree. I have here a simple example of a decision tree with two classes, a binary classification problem. And as you know, a decision tree is going to make recursive splits of the input space into different parts that can be represented in this form or also in the form of a tree. For example, this split over here where the first feature x1 on this axis is bigger or smaller than 9. This represents this line over here. And when we make splits in our decision tree, we're going to partition our input space. And the way to get probabilities out of a decision tree is by looking in each of those splits, what are the frequencies of the different classes. So for example, over here, in this split, I have 1, 2, 3, 4 observations of the black class, 1 observation of the red class. So I have here a probability of 1/5 for the red class. You do this for each of the splits, and in that way you can get probabilities out of it. Now, at this stage, it should already be clear to you that those probabilities that you get out of this might be not really representing the ground truth underlying probability distribution. For example, if we let our decision tree grow till very pure leaves, if you let them overfit, then you will get in each of those different branches like one of the two classes. So you will get either a probability of 0 or a probability of 1 for the red class, and this might not represent your underlying probability distribution. The same problem is going to occur with neural networks. So how do we fit typically probabilities with neural networks? Here is an example of an image of a flower that I put as input to a neural network. I have my feature learning layers, and then typically for multi-class classification, we're going to have a softmax operation at the end. The softmax layer is going to generate me here probabilities for each of the classes. So in this example here, we have 1, 2, 3, 4, 5, 6, 7, 8 classes. There's 2 classes that have a high probability. The other classes have a lower probability. Now, usually those probabilities that come out of a neural network are not always trustworthy, and the reason for that is what happens during training. So the problem during training is that you're going to feed examples to this neural network. For example, here is an example of the third class. So you basically say my underlying probability distribution for this image, py given x, the true py given x is a degenerate distribution where you have a mass of 1 assigned to one class and 0 to the other classes. And so typically you're going to minimize cross-entropy. Cross-entropy can be decomposed into the entropy of the true probability distribution P, and then the KL divergence of the true P and the predicted P. So what you see here is that when you minimize cross-entropy, you want to minimize this difference. KL divergence is a kind of distance measure between two probability distributions. You want to minimize this distance between those two distributions. And since this here is a degenerate one, you're going to go for distributions that are very peaked. So typically, neural networks have the tendency to produce distributions that are like having a very high probability to one class and zero probability to the other class. So that's a consequence of optimizing the cross-entropy loss. So both with decision trees and with neural networks, you can end up with probabilities that don't make sense. And because of that, people have been looking at calibration as ways of measuring whether those probabilities are correct or not. So here I'm showing you two examples of what can happen when you fit machine learning models. So we have here on the horizontal axis the predicted probabilities, and on the vertical axis the true probabilities. So this is here a hypothetical example, because in practice you never know the true probabilities. So both the situation here can happen, where you have like predictions more to the extremes, so you predict higher probabilities than what they really are. Or you can have like a bias to one of the extremes. This typically happens in multi-class classification problems. The second situation. So in both cases, those probabilities are not good probabilities. Ideally, you would like to have them to lie here on this diagonal line. And this brings me to the notion, the definition of calibration. What is calibration? We formally classify calibrated if this thing holds over here. So let's look a bit more closely at this formula. I have a conditioning here. So the easiest way to explain it is to first talk about the conditioning. We condition on all predictions for which the probability of, let's say, the positive class is alpha. So like all the people, all the patients in our medical case, all the patients for which you predict the probability 0.6, for example, or in general alpha, then the probability of observing actually the label 1 should also be alpha for these cases. So it's quite a natural definition, and you can also apply it to other situations that are not machine learning models. For example, in medicine, when a doctor is talking to you and tells you, you have this disease and you have 60% chance of surviving, what does the doctor mean? That for all the patients that he has, for which he predicts 60%, that at the end 60% should survive. You cannot survive 60%. You're either going to survive or you're going to die. But those probabilities are usually based on a certain population. So the way you condition here is you condition on all the cases that have a certain probability. That's the kind of notion that you define here. So we call this the notion of calibration for binary classification. So how are we in practice going to check this? In practice, we can check this with reliability diagrams. So what's a reliability diagram? You take a data set. So usually you do this not on the training data, but on calibration data or a test data set. And we're going to divide our instances for which we make predictions, we're going to divide them into bins. So here in this example, we divided them into 4 bins based on the predicted probability. And then in each of the bins, you observe how many times it was the positive class, how many times it was the negative class. So you need a data set here for which you know the true labels. So in this situation here, it looks quite okay. I have here, so the probabilities between 0 and 0.25, and I observe something like 18 or 20% of positives over there, so that's quite okay. Then I have here between 0.25 and 0.5, so the average of that is like 0.37, and I observe like 40% positive, so that's also quite okay. In this situation here, you see it's not okay. The observed frequencies are much lower than the predicted frequencies. We are substantially under this red diagonal line. So in this second case, this is a classifier that's not calibrated. So for the people in the winter school that need to do a project, this could be like an easy one if you build a machine learning model to make such a reliability diagram and try this out yourself. You can also measure this in a more quantitative manner. So these reliability diagrams are kind of a visual manner of assessing whether your classifier is calibrated or not. If you want to do it more quantitatively, you have something which is called the expected calibration error. So what is this? So this is a sum here over the different bins. So in this example, we had 4 bins. In general, we have B bins. And in each of the bin, you look at the difference between the observed frequencies and the predicted frequencies. So what are the observed frequencies? This is just how many times do you see the positive label. So this is why I here is encoded as 0 or 1. So you just count how many times you have a 1. The predicted frequencies is just the average probabilities that you have in this bin. And then you look at this difference. This difference should be small. And we have a kind of here normalizer for the size of each bin. Some of the bins might be bigger than other bins. If you go for bins of equal width, there's variance of this approach where you take bins of equal frequency. So then this denominator here would cancel out in that case. So this is how you can define this in a more quantitative manner. Now, this is for binary classification. For multi-class classification, there are some extensions of this principle. There's actually 3 extensions, and quite of these have been developed by people here in Scandinavia, mainly in Sweden. So the first extension is called confidence calibration and is the most simple extension, and also the weakest extension in a way. So what is confidence calibration? If you have more than 2 classes, you just look at the highest probability that you predict. So for every instance, you collect the highest probability. Let's say we have 3 classes. In this example here, the highest probability was the probability for class 1. And then we're going to do the binning according to this highest probability. So just as in the previous slide, where you had those different bins, we just take the highest probability for each of the instances. So for one instance, this could be here, like in this example, class 1, and then for another instance, it could be class 2. And you just do the binning once based on those probabilities. Then you have something called class-wise calibration. There you're going to repeat the binning for each class. So there you're going to really inspect all the different probabilities. You first take class 1 as the positive class, the other classes as the negative classes. You do the binning, and then you repeat it for class 2, and you repeat it for class 3. So this is kind of a 1 versus all decomposition, like what is something commonly done for multi-class classification, but we're doing here this 1 versus all decomposition on the level of calibration. And then you have also something called calibration in the strong sense. And in calibration in the strong sense, we're going to do the binning in the simplex. So instead of doing the binning for each class separately, we're going to do the binning here in more than 1 dimension. So on my previous slide, here, the binning was just on an interval. You just bin an interval. These extensions over here is also just binning on intervals. But in calibration, in the strong sense, you're not going to bin on intervals, but you're going to bin on the probability simplex. So here, like this triangle, will be 1 bin, which means basically that you condition on all probability vectors that have a certain value, all the probability vectors that fall into this bin. You look at the observed frequencies versus the predicted frequencies. So that's how you can extend these for multi-class classification. I'm not going to go into the formulas. This becomes quite technical, actually. But let's focus now a little bit on then how, with these methods, we can test whether our model is calibrated. So there have been several statistical tests developed to test whether a model is calibrated. I'm going to explain one of these tests, like the simplest one, which is also applicable to quite a lot of settings, because actually the measure that you use to measure calibration does matter too much in this test. So it's a bootstrap-based test. So how does it work? So we start with repeatedly drawing a bootstrap sample from the original test set. So we're going to do this on a test set. And then in the next step, for each instance X in the bootstrap sample, so you know bootstrapping, this is sampling from the original data set with replacement. So a single observation from the original data set can appear more than once in your bootstrap sample. Can also be the case that it's not in there. Then for each instance that appears in this bootstrap sample, we're going to throw the label away. So we're not going to use the label. And we're going to sample a new label according to this predicted probability distribution that comes out of our model. So our model predicts probabilities. According to those probabilities, we're going to sample a new label for this instance. We do this for all the instances. And so you have many bootstrap samples, so you repeat this for every bootstrap sample. For each of those bootstrap samples, we're then going to measure our calibration error. So I've explained this expected calibration error measure. This could be used. There's many other measures in the literature that have been proposed. But let's say we use this expected calibration error, and we compute the error that we obtain on this bootstrap sample. So we're not using the true labels. We are computing this error with the new labels that we have generated. And why do we do this? We do this because we want to build up the null distribution, the distribution under the assumption that the null hypothesis is true, that our model is calibrated, and we will get a distribution that might look like this blue distribution. Our expected calibration error will not be 0. We have sampled labels. Depending on your sample, you might end up with a higher score or lower score. It will not be 0, but it should be close to 0. And then in the last step, we are now going to use the true labels, and then we compute the expected calibration error with using the true labels. And this might end up, for example, with the red thing over here. And then you just do the standard thing when you do a statistical test. If this red bar seems to be far away on the right-hand side, depending on the significance level that you have chosen. If it's in one of the tails, well, for most of the measures, it's going to be the right tail, because most of these measures are bound by 0, like this expected calibration error cannot be 0, so you only have to look at the right-hand tail. And if it's in this right-hand tail, then you're going to reject null hypothesis, and you're going to conclude that your model is not calibrated. If the conclusion is there that your model is not calibrated, then there's a whole bunch of methods that you can use to recalibrate your model. Also, due to lack of time, I can only discuss 2. So let's think of this situation over here. As I explained already, this was a situation of binary classification. We have on the horizontal axis our predicted probabilities. We have on the vertical axis our true probabilities. They should be matched on the diagonal line, but this is not the case, so this model is not calibrated. These calibration methods, what are they typically doing? They're going to do a monotonic transformation of those predicted probabilities so that they are going to lie at the end on the diagonal line. And there's several monotonic transformations that are possible. So one popular approach is isotonic regression, which is just like taking step functions. Or another popular approach introduced by Melis Creel in 2017 is beta calibration, where you have the shape of a beta function to do this monotonic transformation. And the way you do this basically is, we have those predicted frequencies and we have the true frequencies that you would expect. So basically this is nothing more than fitting a regression model in one dimension, where we have the predicted probability on our horizontal axis here, and these are the zeros and these are the ones. So you're going to make this shape in such a way that the observed frequencies are going to match the predicted frequencies. All right. This is how this was done, let's say, 5 years ago. In recent papers, we see more and more a trend towards not doing this on a separate calibration data set, but during the training already. So in neural networks, there's also tricks to do this during training, this calibration. And the way you typically do this is, for example, a paper from NeurIPS 2022, where you're going to, on the one hand, minimize the risk. So this would be in a neural network just cross entropy. And we're going to make it a constrained optimization problem, we're going to say our calibration error has to be below a certain threshold. So we want to minimize the risk, cross entropy, but we want to have the guarantee that we allow a miscalibration of maximum a certain amount. As you know, a constraint optimization problem of this type can always be rewritten as an unconstrained optimization problem where you introduce a regularization term lambda. So this is an alternative way of optimizing this. And what you need for this is this calibration error kind of measure needs to be something that's differentiable. So this expected calibration error that I discussed with you, this is a method that's not differentiable. You have this binning, because you have those different bins that you have to make. You cannot differentiate this measure. But recently there have been other methods proposed, other measures proposed that are differentiable, and typically you're going to use these into this. So this is only one approach. There have been quite some papers on this recently, so papers that optimize the focal loss or do label smoothing or entropy regularization or kernel-based calibration error estimation, differentiable approximation of binning estimators. There's different names for this in the literatures, but all these methods basically have this idea of, during training, to optimize already for calibration. So this is another approach that you can take. It's difficult to say which of the two is the best compared to what we had on the previous slide. The advantage of the thing on the previous slide is that you do this afterwards, whereas here you have to make this compromise. How much am I willing to suffer in terms of calibration versus optimization of my metric of interest, accuracy-based metric, whereas with the approach of the previous slide, you need to have a separate calibration data set to do your calibration afterwards. So both have advantages and disadvantages, I would say. Okay, these are representations based on distributions. Now in this part, I'm going to talk about representation based on sets, and then I'm also going to discuss the extension to regression. After that, we'll have a second short break. So representation based on sets, there's actually three different paradigms that can be used in that case. Due to a lack of time, I will only explain one. And the basic idea is explained on this slide. So again, let's take this example of this image of a flower that we feed into a neural network with some feature learning layers. We have a softmax output, and this gives us some probabilities. And what we see here in this example is that there's like more than one class that is likely to be the true label. So when we predict sets, what are we going to do? Instead of predicting one label, we're going to predict multiple labels. The most simple way of doing that would be having a fixed number of labels. This is quite popular, like in recommender systems and information retrieval. Think about Google, that gives you not one website when you put in a query, but it gives you multiple websites. We call that top K prediction. Then a framework that has become quite popular in recent years is conform prediction, and that's the one on which I'm going to focus for the next slides, which is a statistical framework that gives you some statistical guarantees about the prediction that you make. And then there have also been some methods proposed that use specific utility functions to predict sets. Actually, I had a PhD student recently that did his PhD on this, but due to lack of time, I will not explain these further. So I'm going to focus on conform prediction. So conform prediction is a framework that has its roots in frequentist statistics and hypothesis testing. And the idea is as follows. If I give you an observation, let's say this image, which might be class 3 or something else, instead of predicting one class, we're going to predict multiple classes. Let's say we say it could be number 2, 3, or 9. And it should contain the true class with high probability. Conform prediction is going to construct such sets so that the true class is in there with a certain statistical guarantee. So you have a guarantee of making less than epsilon mistakes, with epsilon is something that you choose beforehand. And the way this conform prediction works is with a so-called nonconformity score. A nonconformity score is a score that is going to tell you how much a given label is conforming the data. So let's take a look at this simple example over here. I have this data set of different numbers, and I have here this new observation over here. I don't know what the label of this observation is. So let's think, okay, what if this observation would be a 0? Would this be like conforming the data or not? Well, there's no zeros in the neighborhood, so it's quite unlikely that it's going to be a 0. What if this observation is going to be of class 1? It's also quite unlikely because there's no ones in the neighborhood. What's the conformity of being it class 2? That's more likely because we have class 2 observations in the neighborhood of this new object that we get. So you're basically going to check all the different labels that you can assign to this instance, and we're going to compute a nonconformity score. Now, in the literature, there's many nonconformity scores. The most simple one is just using the predicted probability. But it's minus the predicted probability because, for a probability, the higher the probability, the more likely that the class label is, but we want here it to be the other way around. So the lower the score, the higher the score, the more unlikely that this observation has this specific label. So this nonconformity score always takes an observation as input and also a possible label together. So I will talk to you about split conform prediction. Split conform prediction is one way of doing conform prediction. It's conform prediction where you use a separate calibration data set. They also use the terminology calibration in this context to actually define a threshold. And what are you going to do with the calibration data? So for the calibration data, we're going to use the true labels. And we basically are going to make a table. So you have all these observations in your calibration data set. Then we have the label that belongs to that observation, and you compute this nonconformity scores. With those nonconformity scores, we're going to make a distribution of the scores, and then we're going to define a threshold based on our confidence that we are expecting. So let's say we want a coverage of 1 minus epsilon %. That means that we should have here in this distribution a probability of 1 minus epsilon at least, and we're going to place our threshold here, this alpha 0. This is going to be the threshold that we're going to find on this calibration data. And so on this calibration data we have now, because we have this threshold alpha 0, that the sets that we construct are always going to have this coverage of 1 minus epsilon. Because, for 1 minus epsilon observations, if you say, if my nonconformity score is lower than this alpha 0, then the true label is in there from 1 minus epsilon observations. If now our test set comes from the same distribution, that's the assumption that we will have to make in conform prediction. If the test set comes from the same distribution, then also on test data we will have this guarantee. So the sets that we're going to predict for test data are these sets here basically. You take all the labels y hat into your set so that this nonconformity score is under this threshold alpha 0. So that's usually going to be more than one label, can also be one label, but for a lot of observations this might be more than one label. And so if this test data comes from the same distribution as the training data, in that case, we should have this coverage of 1 minus epsilon. Now, to show you that this is only a coverage and expectation, I have a synthetic experiment. It's an experiment done by one of my previous PhD students, Nicolas de Wolf. So what did he do in this experiment here? It's actually two plots. We have once a test set of 3,000 observations, and we have one of 300 observations to see the effect of the test set. And I have here on the horizontal axis the size of the calibration data set. So we use this calibration data set. In this setting here, we wanted a coverage of 90%. And in blue, I'm showing you what the real coverage is that you obtain. I don't remember what the data exactly was. I think it was synthetic data so that you can generate new test sets and calibration data sets. So the red line is 90%. You see you're not always reaching this coverage of 90%. Sometimes you're under it, sometimes you're above it. But on average, you reach this 90%. So that's the guarantee that you get with conformal prediction. On average, you have this coverage level of 90% correctness that you want, but there might be some deviations from it. So in the world of conformal prediction, this can be seen as some sort of epistemic uncertainty. Actually, people have shown that the kind of distribution that you get there over those coverage scores is a beta distribution. And you see if your test set becomes smaller, that it becomes like a beta distribution with a heavier spread. So here, for example, if you have bad luck, then your coverage is really much lower than this 90%. The main reason why I'm showing this is that, people often believe that this conformal prediction is a kind of thing that solves all problems, but that's not really the case. On a fixed test set, you can still have a lower coverage. It's just a guarantee that you get in expectation, basically. Okay, let's now talk a bit about the extensions of regression of the two previous approaches, both the probability distribution, the calibration methods, as well as the conformal prediction methods. So what changes in the regression setting? So in the regression setting, we can also talk about the two things. We can talk about calibration and we can talk about predicting sets. But the main differences are in regression, sets are way more popular than calibration metrics. And two, for classification, our output was a categorical distribution. The distribution that we predict is a fixed distribution. For multi-class problems, it's a categorical distribution. For binary classification problems, it's a Bernoulli distribution. For regression, our spectrum is much wider. We can predict many different types of distribution. So here in this example, I have a simple linear regression example where we have one feature on the horizontal axis, this feature x, and then we predict in linear regression, as you know, we predict a Gaussian distribution. So actually in linear regression, we have four important assumptions. The distribution you predict is a Gaussian one. There's also a linear relationship between the features and the mean of that Gaussian distribution, represented by the blue line over here. Then the Gaussian distribution that you predict should be the same Gaussian distribution for every x. So in the simple linear regression case, we have homoscedastic noise, which means that this variance you have over here is the same for every point x. The mean differs, but the variance remains the same. And then the fourth assumption that you need to make is that those errors that you make, that they are independent of each other. This fourth assumption is like standard for IID data, the classical machine learning assumption for supervised learning as well. But you need to take those assumptions. Now, if you deviate from some of these assumptions, like this assumption of a Gaussian distribution, then you might consider other distributions. So the output that you get will depend on the assumptions that you make. If you have count data, you might consider a Poisson distribution or a negative binomial distribution, and so on. So there's a much bigger spectrum in distributions that you can predict and how you can represent your uncertainty there. So there have been extensions made to do calibration for regression. And for regression, we're going to do this calibration based on the quantiles. So here I'm mentioning two recent papers that are doing this. So what is the definition of calibration for regression? So basically, we're going to consider quantiles. So this Q alpha is the alpha quantile that I consider. And this alpha quantile is going to be a function of x. So I'm modeling different quantiles as a function of x. So if you have like a model that predicts a distribution, you get those quantiles automatically, like with the Gaussian distribution. And then you look at the probability of the label that you observe, whether it's smaller than that quantile. So if you have modeled the alpha quantile, then this probability should be alpha. Then you're calibrated. Now, just as for classification, calibration is quite a weak notion. And in this paper, I think this figure over here is the figure of the first reference. They give a nice example of this. So they have data generated according to this sort of sine curve, and it's a heteroscedastic setting. So the variance increases when x increases. Now, if you fit a linear regression model with Gaussian assumptions, then you get this line. And like the colors represent here, like your Gaussian distribution. So the farther away from it, then this one turns out to be quite calibrated as well, because it doesn't represent the data too well at all, but still it turns out to be calibrated. So how are you going to measure in practice this calibration? You just look at the predicted quantiles, and then you just look at those frequencies that you observe for those different quantiles, like what you would do like for Gaussian distributions with a QQ plot, for example. So this also makes it quite visible that this is calibrated. So let's say if you look at this yellow over here we're maybe at the 90% quantile, and you have a couple of observations that are outside. So actually 90% of the data is under this quantile. So that's a way how you can see visually that actually this is calibrated, but although this linear model is a calibrated model for the data, it doesn't represent the data at all. So the same situation can occur in classification. Calibration is only like a very weak condition. It doesn't mean necessarily that you represent the data in the correct way. So that's about calibration, but actually for regression, I would argue that predicting sets is more popular. And in regression, sets often take the form of a fixed interval. You're going to predict an interval of values, and that's going to be your set. So there's ways to construct those sets automatically. And one way to do that is with quantile regression. So with quantile regression, you can also model the conditional distribution in a non-parametric way. So instead of fitting, for example, the mean, we're going to fit one or multiple quantiles. And the way you typically do that is by optimizing the pinball loss. So I have here my true label y. I have my quantile q alpha that I want to predict. And this is how this pinball loss looks like. So you can use this approach to just predict a quantile, but you can also construct an interval. If I predict like the 10% quantile and the 90% quantile, then I will get an interval, and this will give me a prediction interval. So a bit more formal notation about prediction intervals. So I will use the notation here gamma, which is a function from x to this r over here is the set of all closed subintervals of the real line. So it doesn't need to be a single interval with more complex methods. I don't have a whiteboard here, but like, let's say, a bimodal distribution, then you might have multiple disconnected intervals. But like with a Gaussian distribution, it will be a single interval. What do we want to have of these intervals? We want to have some validity there. They should be valid, which means that for a desired coverage 1 minus epsilon, I want the probability that the true label is in this interval should be higher than 1 minus epsilon. And distribution calibration is a stronger notion because we fix here on a specific epsilon, whereas in distribution calibration 2 slides ago, we were considering all different epsilons, basically. Now, in addition to this validity, you also want those intervals to be small. They should have the coverage, but okay, if you make them very big, then they will always have the coverage. So you also want to have them small. So those two criteria are usually conflicting with each other. And there's many methods in the literature to construct those intervals. So you can do this with like methods that model a density based on Gaussian assumptions or other assumptions, or even in a non-parametric way. You have direct interval estimation methods, like this quantile regression can be used for that. Some people have been using ensemble methods for it, or you can also use conformal prediction to construct those intervals. Due to lack of time, I will only discuss how to do this with conformal prediction. So how do you do it with conformal prediction? In case you have a point estimate, let's say an estimate of the mean, like a linear regression, your nonconformity score that you're going to use for regression is this nonconformity score. It's just the absolute difference between your prediction for the mean, rho here represented, and your true label y. A previous PhD student of mine showed in a couple of papers that actually this nonconformity score is a better nonconformity score in case of heteroscedastic noise, and in case where you can estimate the variance quite well. So here you divide by the standard deviation. So this is a small modification of the previous nonconformity score. If you have a good indication of the variance for a specific point x, then it's better to use this nonconformity score. And in the case where you have already an interval estimator, like with quantile regression, where you would start from an interval, but it might not be like a good interval yet, and we're going to use conformal prediction to improve it. In that case, you might use this nonconformity measure, where this L hat here and this U hat are the lower bound and the upper bound of the interval that you started from. So that's also a popular nonconformity measure that has been used. So let's show you a couple of results. So this was results obtained in the PhD of Nicolas de Wolf. So this is results on 10 data sets. So the data sets are here represented on the x-axis. I've ordered the data sets according to predictive performance. So in yellow, we have predictive performance measured in terms of R squared. Then in blue, I have the coverage, and in green, we have the length of those intervals. So you see that this differs here a little bit. It's not because your predictive performance is better that your length of your intervals is necessarily smaller. By the way, all those data sets were normalized here in terms of the label, so that doesn't have an influence in it. But what you see with quantile regression is that you don't get the coverage that you would like to have. On most of those data sets, we were aiming here for a 90% coverage. You see you're substantially under this 90%, at least for the ones where also your predictive performance is quite low. You see that the coverage that you obtain is quite bad, actually. I would not be so happy with this. What happens if you do conformal prediction on top of it? So this is with this nonconformity measure, because we have already an interval, so we're going to improve the intervals with conformal prediction. What happens then is that you get this. And you see that now we're at this 90% where we want to be. On average, at least, we are there. So this is what you have to see in blue. In blue, we still have the coverage. You see that sometimes you deviate from it, especially for this data set over here. The deviation can be quite substantial. This is perhaps because this might be a smaller data set than the other ones. But we have this guarantee of this coverage of 90%. So that's, again, like the nice thing of conformal prediction, that you have this guarantee on average that you will have a coverage of 90%. So this slide here kind of visualizes quite nicely that by doing conformal prediction, you can improve over other existing methods that are going to construct prediction intervals. So that brings me to the end of the second part, where I talked about first-order uncertainty representation. So I have a couple of take-home messages about this part. So what I try to explain to you is when we limit to first-order representations, there's basically two ways of representing uncertainty, either by means of probability distributions or by means of sets. I would say that both of them are quite popular in the literature. For regression, the sets which become intervals are a bit more popular than the distributions. So I've explained this to you for classification and regression. Of course, there's extensions possible for other machine learning settings. When we talk about this disentanglement of aleatoric and epistemic uncertainty, I would argue that all these methods primarily focus on aleatoric uncertainty, but not exclusively. For example, conformed prediction, there's also an epistemic uncertainty component in it, because if your model is badly estimated, typically your sets are going to become bigger. So it's not purely aleatoric uncertainty. Some of those methods focus on total uncertainty, but there's not a disentanglement of the two types of uncertainty. You just put the two types of uncertainty on one bunch and you measure this as one type of uncertainty, basically. And although those methods give you some guarantees about the uncertainties that you get, I would argue that these guarantees are still quite weak in practice, and you should treat, of course, those results with caution. Okay, that brings me now to the last part. I don't know, should we have another short break here, or I have the feeling that this part was quite small, actually. Yeah, okay, let's go a little bit further and then do another short break. So we will go now to the second order uncertainty representations, and I would like, for the remaining time, explain to you 4 groups of methods. The first group of methods is actually quite an ad hoc approach, but I like it in a way because it's quite simple. I will start with that. And then the other 3 groups of methods, Bayesian methods, ensemble learning methods, and generalized loss minimization methods, which are in the literature better known as evidential deep learning methods. They're a bit more involved. So I will do these then after the last break. So let's maybe come back to this picture that I showed in the beginning to explain you this difference between first order and second order uncertainty representation. So in this first order uncertainty representation, we had machine learning models that just give probabilities as outputs, like this probability vector over here, which might be different from the true underlying distribution that we don't know. So that would be our epistemic uncertainty. Whereas those second-order models, they're going to give you the uncertainty about this probability vector. So they model a second-order distribution, a distribution over these probability vectors that is going to represent how certain we are when we predict probabilities, how certain we are about these probabilities. And the notation that I will use for this, the models that we're going to use, is a model capital H, which is a mapping from X to this set of second-order distributions. Basically, for different methods, these second-order distributions will look different. Okay, I'll start with the simplest group of methods, density and distance-based methods. And for the density and distance-based methods, I would say how you represent aleatoric and epistemic uncertainty is quite straightforward. I have here an example of 4 classes. So what are we going to do with those methods? We're basically going to model a density for each of the classes. So this is a generative model in a way. And then we're going to look for a new observation like this one here. Using those densities, we can predict the aleatoric and the epistemic uncertainty. Does anybody have an idea how you would measure aleatoric and epistemic uncertainty in such a model? Let's say I have this new flower over here that lies over here in the feature space. Does anybody have an idea how you would measure this? If you raise your hand, you'll have to be clear because I have some difficulties to see the hands in the room. Nobody? Yes?
Some divergence measure like Albert-Leibler for probability distribution.
And can you be a bit more precise how you would do this? Yeah, so for epistemic uncertainty, if you want to reduce it, you will get more samples. So like here, this point here, There's indeed very few samples of it, but we're now in a setting where we cannot collect more samples. So actually those methods are also used for active learning. So indeed, collecting more samples is some sort of active learning scenario. Then you will reduce your epistemic uncertainty, but here we are in a setting where the data set is fixed. So for this test observation, would you argue the epistemic uncertainty is low or high? You want to collect more samples, so I assume that your epistemic uncertainty is high here, and this is indeed the case because we are in a region where the density is low. We haven't seen a lot of observations in that area of the space, so our epistemic uncertainty is high. We are in a region where the density is low, so the epistemic uncertainty is high. So we can use those densities to define what epistemic uncertainty is. In regions where the density is low, this is typically regions where your epistemic uncertainty is high. How would you define aleatoric uncertainty? With aleatoric uncertainty, you just look, okay, are there like two densities close to it? If there's like more than one density close to it, then maybe it might be this class or this class. So, yeah, if you have, for example, an observation that ends up here, in the middle between those two point clouds, both the density for the green class and the red class is high, so this might be here an observation of high aleatoric uncertainty. And with distance-based methods, you can do something similar. With a distance-based method, you're not going to model a full density, but you're just going to look at distances. And for example, again here, this observation here might be far away from all those observations that you have in your training data set, so your epistemic uncertainty is high. If you have like an observation that lies over here, then there's green and reds in the neighborhood. In that case, your aleatoric uncertainty would be high. So that's typically how it works with those methods. And in the interest of time, I will only discuss with you like two recent methods. Actually, this idea is already quite old. I found it back in a paper of 1995, actually, of Thierry Deneux. But recently, in a lot of ICML and NeurIPS papers, you have seen this idea applied mainly for out-of-distribution detection. So, for example, this paper over here from 2018, it's quite a simple approach. What does this paper do? It's just going to model a neural network. So first you fit a standard neural network using softmax, and then you're going to do LDA in the embedding layer. So in the penultimate layer, you have your neural network with all those feature learning layers, and then the layer before you apply the softmax operation, that layer, that representation, there you're going to do LDA. So this is a picture that I took from the book of Hasty and Tipshirani. You might recognize this picture, an example with 3 classes. So in LDA, we're going to model a Gaussian per class. It's going to be a Gaussian with the same covariance structure for each of the classes. That's why you get those 3 ovals over here. And how do you represent then your epistemic and aleatoric uncertainty? So as I say, each of those classes is going to be a Gaussian distribution with a mean vector mu j that is specific per class, so it has an index j, and it has the same covariance matrix. Well, we can represent epistemic uncertainty via the Mahalanobis distance, which is this distance measure. So you basically, for a new instance x, you just look at, so you embed it in the penultimate layer, that's this f of x, and you just compute this Mahalanobis distance in this penultimate layer. So if it's far away from each of those densities over here, like if it's here in the space, for example, then your epistemic uncertainty is high. In other cases, your epistemic uncertainty is low. How are we going to model the aleatoric uncertainty? In this case, you would just do this by Bayes' rule. You have a generative model. If you apply the rule of Bayes, you can get the probability of y given x out of it, and you just do this in this penultimate layer. So this is how it works with this method. It's an example of a density-based method. In recent ICML and NeurIPS papers, we have seen alternatives with all fancy generative models going from autoencoders to diffusion models to normalizing flows. So there's many different approaches possible, also like energy-based models are quite popular for this. I will also give you an example of a method that's not going to model a full density, but just a distance. Very similar idea. So this was a paper from ICML 2020, where we again are first going to fit a neural network. Well, in this case, actually the whole fitting is done together. But you're going to, again, consider your feature learning layer of your neural network. So this is a picture from this paper. We have here an image that looks something like between a cat and a dog. So you map it in this embedding space. And then we have a centroid representing each class. So your cat and your dog have some centroid vectors. And we're going to look at distances between this new object that we get and those centroids that we have modeled for each of the classes. So let's say this centroid per class is the vector EJ for the class YJ. And my mapping to the embedding space is this bold F of X. So instead of looking at the distance in this paper, they actually look at the similarity. So you compute the similarity. There's some technical things involved here that you still have a mapping from this embedding space to the centroids via a linear transformation W that's specific per class. Okay, that's a specific thing for this paper. Not very important, but the most important thing is that you compute the distance between this embedding and your centroid, and you convert it here into a similarity measure by taking the exponential of the negative distance. And then you compute the epistemic uncertainty by looking at the maximum of those similarities. So in the previous slide, we had the minimum of the distances. Because we are converting here distances to similarities, it becomes the maximum of the similarities. Now, I wanted to say, how are these methods evaluated? That's on my next slide. Maybe before I get to that, so most of these methods don't really construct a second-order distribution, but some of them do. So for example, this paper from 2021 are using this approach to then model a second-order distribution over the probability vectors. And this is a replicate of a picture from that paper, where I have three classes. I have the number 7, it's a bit small here, number 7, number 4, and class number 1. So let's say we have 3 different digits. And like an observation that arrives here, for example, you feed an image to this neural network, which is just like noise. It's something that was not in the training data, so you end up here in a region where your density is very low. In terms of second-order distribution, you should end up with something that's very close to the uniform distribution over the simplex. This example here, which is something between a 7 and a 1, might end up here between those two point clouds for the two classes. And this will end up in a second-order distribution that is kind of peaked close to where you have an equal probability for those two classes. So you get this kind of second-order distribution, whereas this example is a clear number 7. It ends up in a density region where for only one class where it's high, and it will end up here in the second-order representation somewhere in the corners of the probability simplex. So this is how you can get then second-order distributions with those density and distance-based models, but there's actually not that many papers that do this. For the other methods that I will discuss, this is actually more popular. But then the evaluation. So this group of methods, in most of the papers that you see, they're very empirical in nature. So usually they have extensive experimental benchmarks, and they're usually applied to the out-of-distribution detection setting, which is quite linked to epistemic uncertainty, because for out-of-distribution data, your epistemic uncertainty is high. So typically what you're going to do is you're going to use this epistemic uncertainty measure to detect out-of-distribution cases. Like the situation you have over here, I have maybe in my training data 2 classes, the orange and the blue class, and then in the test data, there's like a new class that appears that's different from the training data, and I want to use my epistemic uncertainty measure to detect this class. So we have had a shift of the data from the training to the test set. There's different shifts that you can consider. So what most people do is what's called prior probability shift. And the formal definition of it is this over here. It means that the conditional probability of seeing the features conditioned on the labels, that this remains the same, but the prior probability of seeing a label is different in the training and the test set. Usually with an extreme case where you have classes that had 0 occurrence in the training data suddenly have a high occurrence in the test data. Not always very realistic, but that's usually how those papers are treating it. And the typical type of data sets that they use are computer vision data sets, NLP data sets. Those usually have many classes, so you might have classes that appear at test time that were not there at training time, and occasionally you also have data sets from the bioinformatics domain. So, as I said, like the most observed special case of this prior probability shift is open set recognition, where you have totally new classes that arrive at test time. So, for example, these classes over here might not have been present during the training time. And it's important maybe here to mention that in this setting, you assume that you don't have any side information about these classes. So there's also generalizations possible like zero-shot learning, where you have side information of those classes, then you will consider other methods. But here we assume that for those classes, we don't have side information, so the best we can do is detect that this is a new class. There's no hope that we can actually make a prediction for this new class. The best thing you can do is just give a flag like, this might be a new class, and I'm too uncertain here. I'm not going to make a prediction for this class. Then some papers also consider another type of shift, which is called covariate shift. And what is this shift? This is a shift formally as follows. The conditional probability of y given x remains the same in the training and the test data, but the probability of seeing a certain feature vector is changing. This could be, for example, happens a lot in computer vision. Let's say you train a data set using ImageNet, very clean images where it's very obvious what the label is, and then you're gonna, at the test phase, give it images from your phone, which might be noisy images, where it's not so clean what the object is, blurry images. So the features have changed from the training to the test data. And because of that, also your uncertainty increases. This is data that you haven't seen during training. It's still the same classes, it's still the same objects, but it's data of a different kind, and you should be able to detect this. So a few methods are also doing this type of evaluation. And then there's the third type of shift possible that's actually in this type of methods never considered. That's another type of literature. And that's the concept drift that you see more like in data streams and time series analysis, where also the conditional probability changes over time. So a typical application would be like fraud detection, where like criminals become more creative over time. So also what's considered as fraud is something that might change over time. Or another situation is like data from different locations. Let's say hospitals, you have trained a model with data from white patients, and then you want to apply it to a hospital in Africa with black patients. Maybe the way a disease works for black people is different than for white people for certain diseases. So the kind of model you have there might not be trustworthy anymore. So in that case, also your conditional probability changes. And in this case, there's more methods like transfer learning and domain adaptation that are used. It's rarely applied to this aleatoric and epistemic uncertainty. And to give you an example that this can become quite complex, I have here a picture of a paper from my group that's still like in preparation. It's an application in bioinformatics where we kind of benchmarked a lot of those epistemic uncertainty quantification methods, not only the ones that I described so far, but also the ones that will be coming in after the next break. And what you see here is a kind of protocol. So it's we did this on multiple data sets, but this is one data set. And here you see what's considered as in distribution and what's considered as out of distribution. So we considered different scenarios. It was medical data of different patients. So it's single cell classification data. You have cells in the body, and you want to predict what type of cell it is based on transcriptomics data. So what happens if we have a patient in the test set that was not in the training data set? Can we kind of flag that with an epistemic uncertainty measure? Or another situation that we considered was where the protocol to measure those cells changes. So you have different type of technologies that can be used to measure these cells. But if we change to a new protocol, will it have an influence on how good we are able to classify the patients? And also, if we go to another part of the human body, if we change the tissue type to another type, this was the third scenario. Now, what these settings have in common is that there's usually like a mix of different type of shifts that occur. You'll go to a different region in the body, so your features will look different, but also you might have different types of cells there. So also the classes will be different. So this is an example of a real-world application where you can get like complex shifts. And what we saw in this paper is that with those epistemic uncertainty quantification methods, to a certain extent, we can detect those shifts, but it's definitely not perfect. Okay, I suggest that we would take a small break here. I'm now moving to the second approach. I have good news and bad news about this last part. So the good news is the shortest part of the three. The bad news is also perhaps the most mathematical, technical part of the three. So I've now, before the break, discussed a first type of approach to represent both aleatoric and epistemic uncertainty. There's three main types of approaches to go. And the second type of approach is Bayesian methods. So to explain Bayesian methods, I have this figure. It's actually a figure made by Eike Hullermeier. Quite some pictures in this presentation were made by him a few years ago. So I've discussed with you about this different levels of representing uncertainty. So we had the 0 level. I had those pictures with 3 classes, but here it's an example with 2 classes to fit everything on one slide. On the 0 level, you just predict either the negative or the positive class. And then on the first level, you predict the probability. So for 2 classes, you can just put your probability on the real line. So let's say the true probability is the green one, this P, and we have the predicted one, the P hat. And since we're now talking about the second order representations, we have an additional distribution over those probabilities. And with Bayesian methods, the way we're going to obtain the second order distribution is by analyzing the posterior. So as you might know from Bayesian methods, you typically start from a prior over the parameters of your model. Let's say we have a neural network, we have parameters. In that neural network, you consider a prior distribution over those parameters. And then you model the posterior, which is in a general notation represented here. So the posterior over the different models given the data D is approximate to the prior over the models multiplied by the likelihood with the data that we have observed. And this posterior over the parameters, so there is really a lot of models that you get. You have like a distribution of models, and each of them is going to give you such a first order representation, and that's how you're going to build the second order representation, basically, by considering this posterior distribution over your different models. So in that way, you can represent and disentangle your aleatoric and epistemic uncertainty. So let's start with like the simplest Bayesian method one can think of, and that's Bayesian linear regression, which is explained in the book of Bishop. So the picture I have here is similar to the book of Bishop. So in linear regression, this is here an example with a single feature. So we have two parameters. We have the intercept beta 0, and then we have the slope parameter beta 1. In this figure, the true underlying model is this one. So that's a model with 0 aleatoric uncertainty. So we start with the prior, which is a Gaussian distribution over those two parameters, beta 0 and beta 1. And when we observe more data, this is what the posterior is going to become. So first we observe a single data point, then a second data point, and here we have observed already quite some data points. And you see that your posterior distribution over the parameters becomes more and more peaked. So this basically represents our epistemic uncertainty on the level of parameters in the model. And that from that, I will explain in a few slides, we can also get epistemic uncertainty on the level of a single prediction for a test instance. So that's for Bayesian linear regression. And now there's quite some Bayesian methods that you can consider. 10, 15 years ago, Gaussian processes were very popular. I will skip these. Nowadays, deep neural network, Bayesian neural networks are quite popular. So we can talk a bit about these. But before we get to that, let's do a bit more formal what we get with Bayesian linear regression. So how does Bayesian linear regression usually works? So I consider a model where I have my observations and my features, and then I have a noise term that typically follows a Gaussian distribution. So the labels y conditioned on our parameter vector and our noise is also a Gaussian distribution. And we can consider the posterior distribution over the parameters as follows. So it's approximate to the likelihood multiplied by the prior over the parameters. And the type of priors you can consider, there's different formulations possible, but like the most common one is this formulation where we have a prior distribution over the beta parameters conditioned on the sigma squared, which is actually here our aleatoric uncertainty term. And this is a Gaussian distribution with mean 0 and a specific covariance matrix. And then for the sigma squared, you can also consider a prior over it. And typically this inverse gamma distribution with two parameters is used for that. Using that, we can construct an analytic solution for what's called the predictive distribution. So the predictive distribution is the distribution over the labels conditioned on a new test instance X. And what do we have in there? We have in there our model that we consider for this new observation X. We have our posterior in there, and but the posterior over the parameters, and then we have also this posterior here for the sigma squared. So what you see here is that you integrate out both your parameters in your model, the betas, and also your aleatoric uncertainty term. Therefore, if you look at the predictive distribution, what does it contain? Usually it contains a mix of aleatoric and epistemic uncertainty. So this first integral is an integral over what we consider our epistemic uncertainty, and the second one is an integral over what we would consider our aleatoric uncertainty term. So if you consider the predictive distribution in Bayesian machine learning, that typically has a mix of the two components. So we will need something more than this in order to disentangle epistemic and aleatoric uncertainty. And most of the Bayesian methods don't go further than this. They don't do any disentanglement of the two types of uncertainties. Now, before I explain how you disentangle this, let's make this step a bit forward and explain you what changes now in a deep neural network compared to Bayesian linear regression. So in a deep neural network, we will consider a very similar model, but it's now not a linear model anymore. So the relationship between our labels and the features is in this functional form f. And in a neural network, we'll have some parameters theta to form this function. We will also have a noise term, epsilon. This noise term represents our aleatoric uncertainty, basically. And usually you also assume that this conditional distribution of the labels given the beta vector and our aleatoric uncertainty is a Gaussian distribution. The consequence of this is that to compute this posterior distribution and also to compute the predictive distribution, we don't have an analytical expression anymore with Bayesian neural networks. So you need approximate inference techniques. I don't have time to go over these. That would be a course on its own. But like the most popular methods for that are Markov chain Monte Carlo, variational inference, or Laplace approximation. The thing I would like to focus on here is how you can get an uncertainty disentanglement in such methods. And actually, although Bayesian methods are quite old, to do this disentanglement is actually quite new. So the first paper that I know that's doing this was a paper of Stefan Depewijk in ICML 2018. And it's what's called an information theoretic decomposition. So since that paper, the paper has quite some citations, this approach has become quite popular. So the idea is as follows. If I have a prediction y, which is, the true label is a random variable, we get this label as a sample from our first order distribution, and the first order distribution is again a sample from the second order distribution. What does that mean if you think about uncertainty? So if we think about the total uncertainty, then this would be the uncertainty of this predictive distribution. And represented by means of entropy, it means that we compute the entropy of this integral. So you first average out all the models you consider on the second level, all the different probability distributions. You end up with one probability distribution on the first level, which is like the average distribution on the first level. And then you compute the entropy of this. So this is nothing more than the entropy of the predictive distribution. We call this the total uncertainty. And then in this paper, they also compute the entropy of each of those models on the first level separately. And they average out these entropies. And so this is a conditional entropy. And this entropy will represent our aleatoric uncertainty. And then the epistemic uncertainty is nothing more than the difference between those two. So the total uncertainty minus the aleatoric uncertainty will give you your epistemic uncertainty. So this is an approach that was introduced in 2018 that has a lot of citations, but recent papers are criticizing this approach in the sense that it's not representing aleatoric and epistemic uncertainty in a faithful manner. And I'm also quite critical about this approach, actually, but it's still like the predominant approach in the literature. I will explain a few slides later some other approaches to measure epistemic and aleatoric uncertainty, but like for this group of methods, this is like the dominant approach that has been used. Before I get to that, let's first explain the other two groups of methods. So ensemble methods is another group of methods that actually has been linked quite heavily with the Bayesian approach. There's quite some heavy links between the two. So what do we have with ensemble learning methods? So you know, in an ensemble, we're fitting different models to the data. And we can also get such a second-order distribution with an ensemble learning method. So let's say we have in total M models that we fit to the data. So each of those models fits a probability distribution on the first level. And then your second level is just what comes out of your ensemble. So you get, in a way, a sample of the second-order distribution. So that's what how those ensemble learning methods are typically interpreted. They are interpreted as you don't model the second-order distribution directly, but you obtain a sample of this second-order distribution. And, well, how do you construct an ensemble? There's many different ways in the literature. I would say there's like 3 popular streams. So in the classical literature, think about random forests. We were randomizing the training data. So you take bootstrap samples of the training data, and this way you get different models, and you do ensemble learning in that way. There have been theories established between Bayesian learning and those type of ensembles. Now in deep learning, we're typically going to randomize something else. So the next thing you can do is randomize the architecture. And a popular approach here is dropouts. There has also been in the PhD thesis of Yarengal a theory established between Bayesian deep learning and this type of randomization. And then another type of randomization that also has become quite popular is do randomization during the optimization. And this is, for example, popular in deep ensembles where you, for example, you start with different random initializations of the parameters in your neural network, and then you run gradient descent. Depending on where you started from, you will end up with a different solution. So this also gives you an ensemble. So those are all different ways of randomizing that will lead to an ensemble representation. So for example, with this dropout, how does this work specifically? Randomly you're going to kick out some neurons in your neural network, and in that way you're going to construct different neural networks, and each of them will lead to a different probability distribution, in fact. So that's how you build up your second-order distribution. What does that mean then in terms of uncertainty quantification? So let's say we have now these M models. Each of those M models give you a probability P theta 1 till P theta M. So you have different parameters in each of those models that you have fitted. And then your integral that you had for the total uncertainty, because we have a sample here, this integral just becomes an average. So you take the average of all these models, and then you compute the entropy. For your aleatoric uncertainty, you had the integral over all the entropies of the individual models. So this now means then the average entropies, and again, you subtract the two from each other to get your epistemic uncertainty. This is actually also the way how it's done in Bayesian deep learning, because we have to sample there as well. For example, with Markov chain Monte Carlo, so actually those integrals are also replaced by expectations, by sums, by taking a sample. So how you do this with an ensemble learning method and with approximate Bayesian techniques is actually quite similar to each other. Then the last group of methods is another group of methods that is connected to Bayesian deep learning, and that has become also very popular in recent years. You have a lot of ICML and NeurIPS papers that are talking about this method. We call them in our tutorial direct uncertainty estimation methods or direct second-order prediction methods, but actually in the literature they're mainly known as evidential deep learning. And how do these methods work? A little bit different. On the second level, they're going to consider parametric distributions. So for this second-order distribution, you will have specific shapes. With the previous two methods, there was not like a specific shape of this second-order distribution, could be anything. But in these methods, it's going to be a specific shape that you get. Typically for multi-class problems, that's going to be a Dirichlet distribution. For binary classification problems, it's going to be a beta distribution. So here, I'm showing you 4 beta distributions in total. So a beta distribution has 2 parameters. If the 2 parameters are 1 and 1, you get a uniform distribution, which means that like all probabilities are equally likely. For the green one here, there the 2 parameters are 5 and 5. The red one, it's not mentioned, and then for the black one, the 2 parameters are 3 and 12. And here you see the probability density function of this second-order distribution. This is already for more than 2 classes. This is the probability density function of the Dirichlet distribution. So we're going to consider such a functional shape. Depending on what problem you have, the type of distributions you're going to consider here will be different. So I'm giving you an overview of what you will find in different papers. So for binary classification, on the first level, it's a Bernoulli distribution, and on the second level, it gets a beta distribution. For multi-class classification, on the first level, you have a categorical distribution. On the second level, this becomes a Dirichlet distribution. So that's then the second order distribution over the simplex. So here you see examples of how this Dirichlet looks like with different parameters. So for free classes, we have 3 parameters in your Dirichlet distribution. So for example, if they are small, then it's still quite uniform. So if they're close to 1, you really get the uniform distribution. And here it becomes more peaked. So this is what you get, for example, with these parameters. So it's quite peaked in the direction of this class. And then you can also do this for regression. So for regression, on the first level, they usually consider a Gaussian distribution. On the second level, this becomes the normal inverse gamma distribution. I've plotted here the picture from the Wikipedia page about the normal inverse gamma distribution. This is a distribution that has 4 parameters. So you model jointly a distribution over the mean and the variance of the Gaussian distribution, which are the 2 dimensions over here. And it's quite small, but for different parameters of this second order distribution, you get different shapes over the mean and the variance of the Gaussian distribution, in fact. Then you have also extensions for count data. You have extensions for multivariate regression. I'm not going to go over these, but again, you will have a first order and a second order distribution in these cases. So what are these methods then doing? You want to model the second order distribution, and they try to do that by minimizing a specific loss function. So in fact, you're going to fit a model that has as input x and as output directly such a second order distribution. And the loss function is of the following type. So your loss function takes as input your second order distribution and the true label. I have here a loss over my n training data points. We call this an epistemic loss function because it models the epistemic uncertainty. So in fact, the arguments of the loss functions are a second order distribution and a true and a label, and it gives you a real number that says how big the loss is. So the crucial question is, can this approach work? With my group, we had last year an ICML paper where we actually claimed that this type of groups cannot represent epistemic uncertainty in a faithful way. And the reason for that is that usually those optimization problems are not well defined. I'm not going to go too much into the technical details, but actually of this shape, there's 2 different variants of it that are considered in the literature, and we show that both of them don't work very well. So the first approach is called outer loss minimization in our ICML paper. And how does this work? So you get a second order distribution as input, here the Q and the true label Y. We're going to sample first order distribution from the second order distribution, and then you're going to have a classical loss function between Y and this P. So in classification, this LA, the aleatoric loss, could be, for example, cross entropy. In regression, it could be squared error. Just a classical loss function, but in order to use a classical loss function, you first have to sample a first order distribution from the second order distribution. Some authors have also called this type of loss a Bayesian loss because it's quite similar to what you would see in some Bayesian papers. And what's often needed is some sort of regularization, and that's where those methods become a little bit ad hoc. So the type of regularization, there's different regularization terms that have been considered, but this one is a popular one where you say, okay, my Q that I consider, that comes out of my model, has to be similar to a reference distribution, which is typically like the uniform distribution. So you want actually this epistemic uncertainty to be high. The question is how to determine the lambda, and that's actually the tricky part. Usually they use out of distribution data to tune the lambda. So if you plug those 2 together, what you get is an optimization problem where you have on the one hand this Bayesian loss. So I've now replaced this Q by this second order model, so this capital H of X is outputting such a Q, in fact. You take this expectation, and then you have this regularization term, and that's what you optimize in this type of approach. In the second type of approach, which is called inner loss maximization, is slightly different. There, you're going to have an expectation inside your aleatoric loss function. So LA, again, is a classical loss function like Ross entropy, like squared error for regression. But we take now the expectation over our second-order models inside the loss function. So in the previous approach, it was outside the loss functions. Here, it's outside, and then you take the average of all those losses, in fact. Here you consider a loss, and inside the loss, you're going to take the expectation over the second-order distributions, again with some regularization term, which might be similar as in the former case. Now, with those parametric families that I discussed, like this normal inverse gamma, this Dirichlet distribution, and so on, usually this red thing, this expectation, can be computed in an analytic form. This is, in fact, just, again, the predictive distribution. And, the problem actually arises there because different parameterizations of your neural network might end up in exactly the same distribution of this kind. So actually, we showed in this ICML paper that this mapping from our second-order model to this predictive distribution, that this mapping is not injective, and that because of that, actually you have different types of models with a different representation of epistemic uncertainty that actually lead to exactly the same model on the first level, and this has as a consequence that actually your epistemic uncertainty cannot be trusted because you have two different models with different epistemic uncertainty because your second-order distribution is different. But on the first-order level, it gives you the same first-order distribution. So in terms of loss, they give exactly the same loss. And because of that, the way you quantify your epistemic uncertainty becomes kind of arbitrary. So how do you actually quantify the epistemic uncertainty in this type of group of methods? So some authors are considering what's called pseudo-counts. I will just show it with an example. So let's say the green one over here, this uniform distribution on the second level, your epistemic uncertainty is high there. If we just sum up those parameters, you get 2. So the value is low. The lower the value, the higher the epistemic uncertainty. For the blue one over here, we have 5 and 5. You sum them up, it's 10. Your epistemic uncertainty is already lower because you have some sort of peak here around 0.5. The black one has a stronger peak. If you sum those two up, 3 plus 12 give you 15. And your epistemic uncertainty is also lower here for the black one. So this is one way of computing the epistemic uncertainty. Then you have also variance-based approaches, which can also be used in for the other methods, like the ensemble learning method. So you just look at the variance of this second-order distribution. You will see the black one has a smaller variance than the blue one, for example. So that's another way of representing your epistemic uncertainty. And then again, you can use this information theoretic decomposition from the previous methods. And for this group of methods, those integrals can be computed analytically as well. For most of the parametric families that are considered, this can be computed analytically. So that's even a third approach. All three have been used for this group of methods. And then typically, once you have this epistemic uncertainty quantified, what those methods also do is then do this type of out-of-distribution experiments, as we explained for the first group of methods. Now, in our ICML paper, we also proposed like a new, more objective way of evaluating this epistemic uncertainty. And we propose to do this via synthetic experiments. So I have here a simple example. It's the example that we also considered in the paper. We consider a kind of model with one feature, and it's a binary classification problem. And we say the Bernoulli parameter conditioned on the feature follows this kind of sine wave. So it's also this green sine wave that's represented over here. That means that, for example, if you say it's a coin that we throw up, here it's quite a high probability that it's tails, whereas here it's a high probability that it's head, and here it's like 50-50. And then what we do is, since it's synthetic data, we can kind of replicate the training data sets. So we sample different data sets of a given size. So let's say for 100 data points, for 500 and for 1,000 data points. And each time we fit a neural network. And what you see here in gray is the different neural networks that you fit. So this is actually your sort of reference or ground truth representation of epistemic uncertainty. We called it a reference representation because you cannot really speak of a ground truth since it's still conditioned on the type of neural network that you use. But at least since you can resample here the training data, you can see what the influence is of working with a small data set. And yeah, you see that the second order distribution becomes more peaked if your training data is higher. So here it's quite wide, the spread. Here the spread is lower. And then if we compared this to what comes out of evidential deep learning methods, we saw that with evidential deep learning methods, you get something that looks very different to what the reference distribution should look like. So the ones you get over here, there's always very peaked in evidential deep learning. I don't remember which approach this was exactly, but you see it doesn't look at all to the gray one. The one over here also doesn't look at all to the gray one. So in that way, we concluded that those evidential deep learning methods are not representing epistemic uncertainty in a faithful way. There's other, I'm coming to the end of my presentation, there's other formalisms possible. So another approach that's getting more popular, I'm not going to go into details, I'm not working on this type of methods, is credo sets. So instead of having a second order distribution in the simplex, you're going to have a set of distributions in the simplex. And each of these distributions could be a candidate for the true underlying probability distribution. In the group of Eike Hüllermeier, there's some people working on this. I'm not going to go into detail on this, but for example, papers of Yusuf Saleh are papers dealing with these. There's some other groups working on this as well. That brings me to the end of my presentation. So I have a couple of take-home messages for this second-order uncertainty representation. So I wanted to convince you in this 2.5-hour tutorial that it's important to represent uncertainty if you want to have reliable predictions. And it's also important to distinguish different types of uncertainty, in particular aleatoric and epistemic, although this seems to be a hard task to do. So for me, at this stage, it still remains questionable whether second-order models will ever be able to represent this epistemic uncertainty in a faithful manner, in the sense that you can really quantitatively interpret those measures that come out of it. In a qualitative manner, it's possible. We have seen in out-of-distribution detection tasks and active learning tasks that the performance can be quite well there. But really, interpreting the numbers is difficult to do. Besides that, I think there's also some other open problems. So what's the influence of the model that you consider? If you have, for example, physics-inspired models where you incorporate domain knowledge in the model, what's exactly the influence on epistemic and aleatoric uncertainty? Also, generalized settings beyond classification and regression, other ways to evaluate this epistemic uncertainty, or even thinking about other forms of uncertainty. These are still open issues